Now let's understand immersed optical system effective focal length. So for immersed optical system, we don't have air on both sides. So here I have a thick lens and I have air on both sides. So the effective focal length is from here to the principal plane of this lens. So I can calculate or measure the effective focal length. But if I have water, or let's say any liquid on the other side, from physical perspective, when the light is propagating through this surface, this interferes between the glass and let's say water. Before adding liquid on one side, you had a huge refractive index change. Let's say for glass, it is 1.5, and for air, it is 1. So you have a big refractive index change. But right now, I have 1.5 for glass and 1.33 for water. So the refraction or the angle is not going to be the same. So the angle is going to be a smaller, or refraction is going to be a smaller. So my effective focal length is going to be something like this. So this angle is going to increase. The distance is going to increase and the angle is going to decrease. So in this case, my effective focal length is different. Now, the question is that how we can calculate the effective focal length of an immersed optical system. So for an immersed optical system, let's say we have N1 for the refractive index of the left-hand side. We have N2 for the refractive index of the right-hand side. And we have N for the refractive index of glass. We have R1 and R2 for the radii of curvatures. And the distance from the first surface to the last one is D. So when you look at this thick lens, you can simplify this lens in combination of two lenses. And as you know, when you have two lenses with focal length of f1 and f2 at distance d, we use this equation for finding the total focal length, which is 1 over f1 plus 1 over f2 minus d over f1 times f2. So all the focal lengths that we put into this equation, we have to use with the sign. And we have sign convention for f1, f2, and all the parameters in optics. Now, if you fill this distance with a material with refractive index of n, like glass, then we have to use a reduced distance, that you divide the distance by n, which is the refractive index. So the equation is 1 over f1 plus 1 over f2 minus d over n over f1, f2. I have this equation. Now I need to find f1, f2. And we know that for a surface with radii of curvature of r1 and radii of curvature of r2 on the other side, the optical power, or 1 over f1, is equal to n, the refractive index of the second material that the light is propagating, minus the refractive index of the light that is inside of that material, which is n1, over r1, which is the radii of curvature of this surface. So we're going to use the same rule for this side. So the refractive index of the next material when the light is propagating in this direction, minus n, the material that light is inside, over r2, which is the radii of curvature of this surface. So you have two lenses actually, f1 and f2, at distance d over n, reduced distance. So we can combine them using this equation. So by combining these two lenses into this equation, we can get to this somehow complicated equation, which is n minus n1 over r1 plus n2 minus n over r2 minus d over n 1 over r1 r2 n minus n1 n2 minus n. So we should be very careful about the sign conventions for all the parameters that you can see in this equation. And we're going to use this effective focal length a lot to the rest of the lecture. So please pay good attention to this way of calculating the effective focal length.